Okay, we're beginning the last section of Chapter 9 in Algebra, Section 9.8, where we will factor polynomials completely. So we're going to see larger, more complex polynomials, four-term polynomials today. And we'll begin by focusing on common binomials. That's the theme of the day, common binomials. This is already partially factored. We can still call it a polynomial. But what's the first thing you think of when you see this kind of expression here? Just this first half, or just the second half. What is it that comes to mind right away? Distributive property, right? And so what else do you notice in this expression about these two pieces?
They're the same.
They have something in common, don't they? They both have x minus 3. So can anybody imagine a different way this could be expressed? Since 4x and positive 5 are both being multiplied to x minus 3. Is there another way? Okay, Cameron, say it.
4x plus 5 in parentheses and then x minus 3 squared.
Very good. That's right. And so if we think about this, in this case here, the 4x could be multiplied, due to our foiling, right? Would be multiplied to x minus 3, just as it was done in the first statement, right? And then the 5 will be multiplied to x minus 3, just as it's done in the first statement. So this is a different way to express the original statement. And it looks like what we're used to seeing in this chapter, the two binomials that you would end up foiling, right? Okay. Before we go on to the next one, because you thought of this first statement as, the first thing that pops into mind is distributive property, another thing a person might do is just distribute, right? And so if we distribute this, what do we get? 4x times x. And here. And here. And here. Could I write this expression this way too?
Yeah.
I could. And then you see that there are like terms? I mean, that's what we get when we go outside, inside. We often get like terms that we could combine. But I could just leave it this statement too, right? So there's so many ways to write these things. And ultimately, we're going to get longer polynomials, and we have to somehow get here today, okay? Higher degree things. This one's a little bit trickier. So what do you notice about the two binomials in this example B? I mean, are they the same? This one says y minus 5. Could this one also say y minus 5?
No.
If we move this around a little bit, if we use our commutative property of addition, we have to carry the sign with us, right? So if we change this one to have highest degree first, what does it look like in there? Negative y plus 5, right? Okay, we have the negative 3. So here's what it looks like if we put this second term in standard form with highest degree first. So it still doesn't look exactly like the first binomial, y minus 5. Is there something we could do to it so that it looks like y minus 5? Hey.
Multiply it by -1.
Good. So really these are opposites. And we know with opposites, if you multiply one of them by -1, you'll get the same number, right? So if we leave this stuff the same, the first term, y minus 5, right? And in this second term, we have negative 3. We pull out a -1, just like we did with our negative a's. And we just did this in the homework with the negative 16t squared. We pulled out a -1, right? So we have negative 3 times -1. Inside each of these terms is now the opposite, right? -1 times y is negative y. -1 times -5 is positive 5. So this is an equivalent expression. But what can we call negative 3 times negative 1?
3.
We can call that just positive 3. And if we bring this other stuff down, now we're back to looking like we were looking in problem A, right? Where we have two terms that both are being multiplied to y minus 5. So I'm sure you could finish this by giving me the two binomials, right? I mean, the second binomial is really easy. They're both being multiplied to y minus 5. But what is being multiplied to y minus 5? Matthew?
2y squared plus 3.
Plus 3. Good job. So you can see this is a little trickier, isn't it? You have to kind of see, oh wow, these two things, you know, these were opposite, so I can pull a negative 1 out and end up with the same. Okay? Okay, we're going to now look at some 4-term polynomials, and we're going to factor by grouping, recalling what we just were reviewing with the distributive property. Okay, so before we kind of review what we're doing, let's try this. We have a 4-term polynomial. They are all different degrees. Do you see that? We have, what is the degree of this term here?
3.
3rd degree. This one? This one?
First.
And this one?
0.
0 degrees. So if there was an x here, it would be x to the 0. And x to the 0 equals 1. So 16 times 1 is 16. It's constant. Okay? So we like them to be in, this is standard form, highest degree to lowest degree. So leave it in, or get it to standard form if it's not. We're going to see that in a moment. But once we do, we can kind of group it. Let's look at these first two terms. So we don't have to have parentheses around these, but we could put parentheses around these. We have x to the 3rd plus 2x squared plus 8x plus 16. So we're just going to look at these as two groups. And honestly, they're going to be really kind to you and give you really nice and friendly 4-term polynomials. Okay? So look at the first two terms. What do they have in common? What's their GCF? Kyle? They both have what factors? They both have 1x? Or do they have more than 1x? They both have more than 1, right? How many x's do they both have? So you would say x squared, right? X squared is the GCF. And give me the binomial that you would have to multiply x squared to get back to this original. Plus x squared times what is, good job, 2. X squared times 2 is 2x squared. So there it is. Okay. Plus, what is the GCF of 8x and 16? 8. Okay, so if we pull out the 8, what do we have left?
X and 2.
X
plus 2.
Good, plus 2. So here we are, right back to the previous page, right? We have x squared multiplied to x plus 2, and 8 multiplied to x plus 2. So let's write this as two binomials, right? And so can you finish that for us? What are the two binomials, Jack? If we distribute right now, we're back right up to where we were before, and we don't want to be there. I want two binomials that are equivalent to this statement here. We just did this here. They both were multiplied to x minus 3, so we brought 4x plus 5 together. Okay, so what will we bring together here?
The x squared and 8.
Plus 8 times...
That's 2.
Good. Good job, that's it. So again, the x squared is still being multiplied to the x plus 2. There it is, right? The 8 is still being multiplied to the x plus 2. There it is. So we now have a completely factored form. Okay, so the note here says group your polynomials with 4 terms into 2 groups of 2 terms, which is what we did here. And then look for the common binomial factors. Okay, let's do it again. We're going to kind of group the first 2 terms together and the last 2 terms together. They have some common factors. So, Sabrina, what's common about the first 2 terms?
R.
So we would have R times what?
R times R plus 4.
Good. And then how about the second 2 terms?
S.
Good. S times what?
S times R plus 4.
Good job. Okay, so we notice that both of these terms are being multiplied to the same factor, R plus 4. So how could we combine those 2 terms, Sabrina? Okay, good. So we have R plus S times R plus 4. Okay. And the final little note is this. When we look at this 4-term polynomial, what do you notice? Matthew?
It's not in standard form.
Good. It's not in standard form. So what will we do? What is the property? I hear you saying put it in standard form. The what? Commutative property of?
Addition.
Addition. Awesome job. You guys are good. We're going to rearrange using our commutative property of addition. And I have this highest to lowest degree, right? That's standard form, highest to lowest degree. So who can give me this in standard form? How about Kyle? What's the highest degree term? Okay, and the next highest?
2x.
It's positive, so plus, and then the next? Good job, negative 5x, and the next? Negative 10. So it's the commutative property of addition because you have to carry the sign with you if it's negative. And there we have it. So now we can go back to grouping. Be careful when you group this because I have x cubed plus 2x squared plus a negative 5x, okay? Plus a negative 10. I'm keeping the negative inside my group. And now we're looking for the GCF. So Vivian, what's the greatest factor I could pull out of here?
X squared.
Good. And what would we have left?
X plus 2.
Good job. And then what's the greatest factor we could pull out of here?
5.
Okay. Negative 5 is a good one to pull out because I want to end up with x plus 2, don't I? So you use your previous factor to anticipate what's coming, right? And we would have x plus 2, which is what we want. Yay. And so could you finish it?
X squared plus negative 5.
Or we could just reduce it to negative 5.
X plus 2.
X plus 2. Good. Okay. So when you get to this point, you have to ask yourself, is there any more factoring I could do? Is there any more factoring that you can see? Now, what if this 5 was a 9? So you would have the difference of 2 perfect squares. So you'd end up with sum and difference. So watch for that in your assignment. I'm sure it's going to pop up. It's a fun extra little bit of factoring you get to do. Okay? Are you having fun? Are you having fun? Oh, yeah. Okay, time is short, so if you're doing this on video, come back and check your answers. Pause it. Come back and check. There's not time to walk through them for the video, but we'll walk through them in class. Okay, this is here because the x minus 2 here did not have a factor in front of it like we've seen. So we could put the invisible factor 1. We have one of these things, right? Which is what Tom did. And then we have x plus 1 times x minus 2. Very good. Okay, so factor the first term, a squared out, and then the second term is one of those, leaving us with what you see. Good job. Okay, so we put this in standard form, pulled out y, pulled out 2, and ended up with this factorization. Very good. Okay, so your assignment is here. Have fun. It's fun stuff.